It was called the Iron Dam. Reinforced in the 1950s, Banqiao was considered exceptionally strong, a massive earth-filled dam holding back hundreds of millions of cubic meters of water on the Ru River in Henan province. Then, in August 1975, Typhoon Nina stalled over the region. Rain that would normally fall over an enormous span of time arrived in just days. In the early hours of August 8th, Banqiao was overtopped. The dam failed, and once it did, the disaster spread through the flood control network. More than 60 dams would eventually fail. Banqiao was not destroyed because it was simply weak. It was destroyed when the conditions behind its design assumptions were exceeded, and the systems meant to compensate could no longer keep up. Banqiao was not just a wall holding back water. It was a system built around hydrological calculations, discharge infrastructure, operators, communications, and warning procedures. Every one of those layers was supposed to provide protection when the water rose. But when Typhoon Nina pushed the system beyond the conditions it had been designed to handle, those layers began failing together. And that is where the real story of the Iron Dam begins. Banqiao Dam was constructed on the Ru River in Henan province as part of a much larger flood control program. The region had experienced devastating floods, and the Chinese government was building a network of reservoirs intended to control water, support irrigation, and drive economic development. Construction began in 1951 and was completed in 1952, with assistance from Soviet consultants. Banqiao was an earth-fill structure, built around a central clay core with compacted fill forming the main body of the dam. It was later reinforced and raised after cracks appeared in the structure and concerns emerged about its discharge infrastructure. After those improvements, Banqiao developed a reputation for exceptional strength. The nickname followed, the Iron Dam. But strength was only one part of the equation, because a dam does not have to survive every flood imaginable. It has to survive the floods its designers believe are realistically possible. And that belief determines almost everything that follows. How much water the reservoir can hold, how quickly that water can be released, how much freeboard remains before overtopping, and how much uncertainty the system can absorb before the calculations stop being useful. That last question would become critical in August 1975. A dam cannot be designed to withstand every conceivable flood. Engineers have to estimate how extreme conditions could realistically become. Those estimates draw on rainfall records, river measurements, geography, and statistical modeling. The result becomes part of the invisible architecture of the dam. It determines the reservoir's capacity, the required discharge capacity, the amount of freeboard, and ultimately, how much protection exists between an extreme event and catastrophic failure. Banqiao was designed around defined hydrological limits, with historical accounts and later analyses describing its flood protection in terms of high return period events, including a figure commonly associated with a 1 in 1,000 year flood. But a return period is easy to misunderstand. A 1 in 1,000 year flood does not mean an event that happens only once every 1,000 years. It represents a statistical estimate of probability. Roughly a 1 in 1,000 chance of an event of that magnitude occurring in any given year. And that distinction matters, because the model depends on the evidence used to build it. If the historical record does not contain an event comparable to what eventually occurs, the mathematics can appear perfectly reasonable, while the physical system remains vulnerable to conditions outside the model. There was also a human dimension to those assumptions. During the rapid expansion of China's reservoir program, technical decisions were being made within an environment that placed enormous emphasis on infrastructure development and increased water storage. One hydrologist who repeatedly argued for greater caution was Chen Xing. Chen advocated more conservative flood control approaches and raised concerns about the consequences of dam failures and the adequacy of discharge infrastructure. According to reported accounts, when Chen proposed a more cautious design for one reservoir project, including additional outlet capacity, officials considered the approach unnecessarily conservative. His recommendations were reduced, he was criticized, and he was eventually removed from his position. The evidence does not support the claim that Chen predicted the exact Banqiao disaster. He did not. But his story reveals something important. The problem was not simply that one engineer was ignored. It was that the system had difficulty accommodating technical caution when caution conflicted with larger development objectives. Greater storage was valuable. Additional safety margins were harder to justify. And once those decisions became embedded in the infrastructure, changing them became far more difficult. The assumption was no longer just a number on an engineering calculation. It had become part of the system itself. On paper, Banqiao had a defined discharge capacity. Its gates and spillway infrastructure had been designed to release large volumes of water when reservoir levels rose. But the capacity written into a design is not necessarily the same as the capacity available during a crisis. Sedimentation could reduce effective storage. Maintenance problems could affect infrastructure. And operational limitations could become much more serious under extreme conditions. That created a dangerous gap between the theoretical system and the physical system. On paper, the numbers could still look reassuring. In reality, the margin was smaller, and the storm was about to test every part of it at once. Typhoon Nina made landfall on the Chinese coast around August 4th to 5th, 1975, before moving inland toward Henan province. Then something unusual happened. The storm encountered a cold front and stalled. Instead of moving rapidly through the region, Nina remained concentrated over Henan and continued producing rainfall across the same catchments. The rain did not arrive as one dramatic burst. It accumulated, hour after hour, day after day. At the most severely affected locations, total rainfall reached approximately 1,600 millimeters over the course of the event, with exceptionally intense rainfall concentrated around August 7th and 8th. To understand what that meant, consider the scale. Some parts of Henan would normally receive roughly 800 millimeters of rainfall across an entire year. Nina produced around twice that amount in only a few days in the worst affected areas. At Banqiao, the reservoir began rising rapidly. Operators opened the discharge gates. But water was entering the system faster than it could be released. The reservoir kept rising. And with every additional meter of water, the margin between controlled operation and overtopping became smaller. The system had entered a race. Water was coming in faster than the dam could get rid of it. But water was not the only thing the system needed to control. It also needed information. Operators needed weather data. Authorities needed updates from the dam. Emergency decisions depended on communication between different levels of government and water management agencies. And communities downstream needed warnings. As the storm intensified, those communication systems began to fail. Telephone lines were disrupted. Links to weather stations were severed. Reports could no longer move reliably between the people observing the disaster and the people responsible for responding to it. The system was losing its eyes and ears at exactly the moment it needed them most. Then there was another problem. There was no fully developed emergency framework capable of guaranteeing that warnings would reach every downstream community quickly enough. An evacuation order was issued for people in the immediate vicinity of Banqiao. But enormous populations further downstream were not evacuated before the flood arrived. Survivor and researcher accounts describe attempts to warn people using signal flares and gunfire. These were desperate measures, but they were being used against a flood moving through darkness at extraordinary speed. The warning system had not simply vanished. It was never designed to cope with a disaster moving at this scale. By the early hours of August 8th, the reservoir had risen beyond the level the dam could safely contain. Water began overtopping the crest. For an earth-filled dam, that is a critical failure condition. Water flowing over the crest begins eroding the downstream face of the embankment. As material is removed, the breach becomes larger. A larger breach allows more water through. More water creates more erosion. The process feeds itself. The dam was no longer simply holding back the flood. The flood was now dismantling the dam. Banqiao failed. The breach released an enormous flood wave into the river valley below. Later engineering analyses have estimated peak discharge from the breach at approximately 78,000 cubic meters per second. That figure was not directly measured during the disaster, so it remains an engineering reconstruction rather than a precise observation. But it conveys the scale of what was released. And then the disaster became something much larger than the failure of one dam. Banqiao was part of an interconnected flood control network. Downstream reservoirs were already under extreme pressure from the same storm. Then the Banqiao flood wave arrived. Structures that had been designed to work as part of a controlled system were suddenly being hit by conditions far outside normal operation. Henan Dam failed. Other reservoirs failed. More than 60 dams ultimately failed during the disaster. The network that had been designed to distribute and control water was now transmitting the consequences of failure from one structure to another. One failure became a cascade, and the system no longer had enough capacity to stop it. The flood spread across approximately 12,000 square kilometers. More than 10 million people were affected. Millions of homes were destroyed. But one of the hardest facts to establish is the number of people who died. Reliable information was not openly available for decades, and different sources have produced dramatically different figures. Some accounts cite approximately 26,000 direct drowning deaths based on official figures from the period. Other researchers, using Chinese sources and including deaths associated with disease, famine, and the prolonged aftermath, have estimated a total toll somewhere between approximately 170,000 and 230,000. Those numbers remain disputed. But the uncertainty should not obscure the scale. By any credible measure, the disaster was catastrophic. Entire communities were swept away. Survivors were left without homes, food, or functioning infrastructure. Disease spread through the aftermath. And outside China, the full significance of what had happened remained difficult to establish for years. The flood itself lasted hours. Its consequences lasted far longer. But Banqiao had another failure, not a structural one, an information failure. For years after the disaster, detailed information about the Banqiao and Henan failures was difficult for the international engineering community to access. Those who lived through the disaster knew what had happened. But outside China, the evidence remained fragmented, incomplete, and difficult to independently assess. That mattered for a reason, extending far beyond historical record-keeping. Engineering advances through failure. A disaster reveals where calculations were wrong, where procedures were inadequate, and where supposedly independent safety layers were actually dependent on one another. The lesson is then supposed to travel. From one failure investigation to the next design. From one engineer to another. From one country to another. But when the evidence cannot move, the lesson cannot move either. The physical disaster happened in 1975. The engineering community outside China would have to wait years before the full significance of Banqiao could be understood. So what actually failed at Banqiao? Not one thing. The first failure was the assumption about the extreme conditions the system needed to withstand. The storm then exceeded those assumptions by an extraordinary margin. The second failure was capacity. The discharge infrastructure could not remove water as quickly as it was arriving, while sedimentation, maintenance, and operational constraints reduced the margin that existed on paper. The third failure was information. As the storm intensified, communications deteriorated, reducing the ability to coordinate decisions and distribute warnings. The fourth failure was the network itself. Once Banqiao failed, the flood wave entered downstream structures that were already under severe stress. The result was not a single dam collapse, it was a cascade. And beneath all four failures was the same problem. The system had too little margin. A robust safety system does not depend on every assumption being correct. It assumes that some assumptions will be wrong. That is why critical infrastructure uses redundancy, spare capacity, independent warnings, emergency procedures, and alternative communication channels. When one layer weakens, another is supposed to compensate. At Banqiao, several layers weakened at the same time. And once the first major structure failed, there was no longer enough capacity in the network to catch the next failure. That is what turned an extreme storm into a system-wide catastrophe. After the disaster, China undertook a major reassessment of dam safety. Older structures in the affected region were reinforced, modified, or evaluated against revised flood requirements. Banqiao itself was reconstructed and later certified as a rebuilt structure designed to revised standards. But the lasting lesson was not simply that dams needed to be stronger. The disaster exposed a broader requirement. Design assumptions have to remain open to challenge. Flood estimates need to be reconsidered when new evidence reveals the limits of historical records. Discharge capacity has to be maintained in the real world, not simply specified in an engineering document. Communication systems have to function during the conditions they are supposed to protect against. And emergency warnings have to reach the people downstream, not merely the people operating the dam. A stronger structure can reduce risk. But if the assumptions surrounding that structure remain unquestioned, the vulnerability can simply move somewhere else. Banqiao is often remembered as a story about an extraordinary storm, and the storm was extraordinary. But extreme events are precisely why safety systems exist. The important question is not whether engineers could have predicted Typhoon Nina's exact behavior. They could not. The important question is how much uncertainty the system could absorb when reality moved beyond the model. At Banqiao, that margin disappeared. The rainfall exceeded expectations. The discharge system could not compensate. Communications deteriorated. Warnings could not reach everyone in time, and one structural failure became a network-wide cascade. The lesson is not that engineers should predict the impossible. It is that critical systems must remain capable of surviving the unexpected. The Iron Dam was not weak. That is what makes this story so uncomfortable. It had been reinforced. It had been trusted. It had protected communities for years. And the calculations behind it were not obviously absurd. They were products of the information, engineering practices, and institutional environment available at the time. But a calculation can be reasonable and still be wrong about the world. And a warning can be technically correct and still be powerless if the system around it refuses to act. That is the deeper failure hidden inside the Iron Dam. Not simply in the earth-fill embankment, not simply in the discharge gates, not simply in the rainfall calculations, but in the space between what the system assumed could happen and what reality was capable of producing. Banqiao shows what happens when those assumptions are tested simultaneously, by a storm beyond the expected range, by infrastructure with limited remaining capacity, by communications that fail under pressure, and by a network with nowhere left to absorb the consequences. The dam did not fail in isolation. The system failed with it, and that is the question Banqiao leaves behind. Not whether anyone could have predicted the exact storm, but whether the people responsible for the system had enough freedom, enough information, and enough safety margin to challenge what they thought they knew. Because every critical system is built on assumptions. The dangerous ones are not always the assumptions that look unreasonable. They are the ones that become so normal that nobody is allowed to question them.